Hello everyone, this is the solution video to homework 1. Now, we had basically 5 questions where we had a heating plant with a given transfer function of a third order. And we were asked to design a controller that ends up in 4 seconds settling time and 10% overshoot for step type inputs. And an important part was the fact that it's going to be a reference tracking problem, which means that if we apply a certain type of input, in this case step type input, we expect the output to try to follow it the best it can. And throughout your solutions, you were asked to give the design steps and equations and stuff like that, especially since you're designing a controller, the ZPK form, TF form of a controller, and also the TF and ZPK form of the closed loop transfer function. And of course, step response and step info pole zero map. All these sorts of documentations were needed for each question, except Q2, I guess. So let's dive into it. Well, the first question was to design or propose an open loop controller that regulates the heat as desired. And here, this as desired part is kind of the thing that you had to think about. Now, there's already an established open loop controller design strategy. The open loop is we have a controller and the transfer function itself, and that's basically it. We apply a reference input to it, then we have a control signal or input, and then we have the output. And ideally, we would like to have y equals r. So that's ideally. And that can be converted into y divided by r in terms of a transfer function, and that becomes equal to 1. So if you're trying to design an open loop controller, then what you're after is basically y divided by r should be equal to 1. And this brings us to the following point. We have f times gs, so fs times gs, and this should be equal to 1. This is only possible with a controller that looks like 1 divided by gs if gs is invertible. Of course, what this means is that if gs is a stable transfer function, its inverse is a stable transfer function also, then we can use the strategy or apply the strategy, because otherwise we will have a pole zero cancellation on the right half plane, which is a bit dangerous and not practically possible to do. So therefore, the system and the inverse of the system should be stable so that we can use this as a strategy. What this means is, and we're going to see what it means, but this is basically pole zero cancellation. We cancel all the poles of the open loop system with the zeros of the controller and vice versa. So also the zeros with the controller poles, and we end up in the magical gain 1, which basically then causes the system to track its input, but of course ideally. If we have disturbance, if there's noise, if the model doesn't represent the system, then we might be in trouble. But another thing is that in this scenario, we are not asked to come up with a controller that has closed loop transfer function 1. Not only. It should also have 4 seconds of settling time and 10% overshoot. So this kind of is a mixed match of the controller design strategy that we are after and the open loop. So we kind of have to mix them together. So what this means actually is that since we have zeta and omega n, let me directly calculate them. So zeta is minus log overshoot divided by the square root of pi squared plus the logarithm of overshoot squared. And then we have omega n, which is 4 divided by ts times zeta here. Now you would argue that this isn't the original formula for overshoot and settling time. You would be right, but these are basically the inverse formulas that you also have to know, because we are given an overshoot value and I need to convert it into a zeta value. We are given a settling time value. We should be hopefully converting this into omega n or zeta or both. In this case, we have TS equals 4 divided by zeta omega n, and I transformed it into this one here. So let me comment this part out. Now, if I run this, we see that the zeta value is 0.5912 and the omega n value is 1.6916. Now, we kind of want to form a polynomial. Usually we do this in controller design, not for open loop, but for closed loop. And our ideal transfer function, or a transfer function that has this behavior, is actually, or has actually, this characteristic polynomial. So if we have zeta, if we have omega n, if we know that the system should behave like that, we can basically state PDS, the desired polynomial, that looks like s squared plus 2 zeta omega n s plus omega n squared. And yeah, we should come up with a system that looks like this, and we're almost there. So what would be the best system to come up with? Well, let me bring it down here. This would be actually something, and then the characteristic polynomial, 2 times zeta times omega n, and then omega n squared. Now, since this is a reference tracking problem, since we want to have a DC gain of 1, we should plug in omega n squared here. So this is the first usage of the reference tracking problem statement here. Because if you use the final value theorem for step type inputs, you will see that the output will settle down to 1, and this is exactly what we want. And furthermore, we want to have the open loop system or control strategy to behave like GSD. Or in other words, instead of having this ideal 1 as a transfer function, we could basically substitute it into GSD. Or let's call it TSD to indicate that this is sort of a loop transfer function. Maybe not closed loop, but yeah, at least it is something. So you can see now that we will, or we're trying to achieve this y divided by r transfer function, TSD. And if this is the case, if we apply step to this transfer function, you will see it will have 10% overshoot and 4 seconds of settling time. So that's nice. But you can see that in order to be able to do this, the controller should have the inverse of the system and TSD, these dynamics, so that we end up in canceling out the system poles, and we're only left with these poles here and with the appropriate gain here. So I'm going to basically use this relation here to design my controller, and let's call ZPKFS. Since we want to also have some documentation for preparing the report, what we can do is we can just leave some semicolons left out so that it generates some output or relevant stuff that we can then convert into our report. Now, this would be then fs times gs, and I'm going to use zpk_ts. And yeah, let us actually prepare a figure. Hold on, maybe grid on, and yeah, x label would be then, oh no, x label would be then time, y label would be then yt, and title would be step response, and x1 is GCA if we need it, but seems like we don't need it now. So y, t, step, ts, plot, t, y, line width, let's have it black, line width of 2. Yeah. And we could also have info equals step info ts, and then maybe TSE is info dot settling time, and OSE is going to be info dot overshoot, so that we can actually create or update the title with ts plus and then string TSE and then plus overshoot plus string overshoot plus percentage maybe. So let's run this, and you can see that our figure has basically the response that we're looking for. Now here you can see 10% overshoot is there, but we still have slight issues with the settling time formula with its correctness. But yeah, this is the best we can do for now, so we're going to stick to it. So this is basically the step response of an open loop control strategy, where the open loop controller has all the open loop poles, it cancels them out, adds our dynamic that we need to have in order to have this output here, and also the appropriate gain so that we are tracking the input, whereas the steady state error is becoming 0. You can try this out without having PDS, just by using the inverse, but then you will see this step type output, which isn't practical and is also not maybe something that we want, because that is not possible. So yeah, this makes more sense if this is an open loop controller. Of course, yeah, this open loop controller has too many poles and cancels them out, but yeah, it is what it is. So this is the best we can do in terms of open loop control strategy. This kind of combines the control with the inverse for open loop control strategy and the desired polynomial or the time domain behavior polynomial connection. That's kind of also mixed in here, and you can see why. Because we cancel everything out, the only thing that's left is basically the desired behavior, therefore the poles of that. So hope that this did explain it very well, and hope that I could answer all the questions related to Q1. So let's move on to Q2. Of course, we could also have pole 0 map here. If you want, we could edit, and it will just show this fact that 5 and 5 is cancelled, 2 and 2, 1 and 1, and we're left with the desired ones, so I left it out for now. So let's transition into Q2. Now here the question is the following. We are asked to find the stability interval using the substitution S equals j omega. Now, of course, our locus is kind of a hint for this question, if you think about it, because, well, it's about the p-type controller. The system on its own is stable, and we cannot question the stability of this, or this hasn't an interval for it. So all that we can do is maybe come up with a p-type controller and examine its stability interval. So that makes more sense than just talking about the system itself. So you don't really have to substitute S equals j omega into GS itself, which by the way is also possible, but we're looking rather at the closed loop behavior of it, where the controller is just a p-type controller. So let's do that actually. I guess I have GSS, so let's define sims k real, and let's have the closed loop here. The closed loop would look like k times GSS, and then divided by 1 plus k times GSS. Then we would end up in PZS, PCS being num then TSS, and then we would look at PCS. So this is basically PCS, or the characteristic polynomial of the closed loop of this system. Now, all that we have to do is use this polynomial and use the given substitution here. So what I'm going to do is I'm directly going to define sims omega real and call it pj omega, for example, and use the substitution here. Instead of PCS, instead of S, plug in 1i times omega. So this is j omega in MATLAB. So all that we do here, maybe we should print it out now, is we substitute this into the polynomial. So what does it mean? Well, if you think about it, we have actually sigma plus j omega in the S domain. And if we restrict it only onto S equals j omega, it means that we don't have a real part. We will end up in the imaginary axis on the S domain. And the imaginary axis is actually the axis which is called the marginal stability point, or margin even. If we pass through j omega, if we are on the right half plane, we will be unstable. If we are on the left half plane, we will be stable, but we are close to the marginal stability bound. So if we plug in S equals j omega, we assume only the poles that are on the j omega axis for the closed loop polynomial, and we substitute it into the polynomial, which means that it is going to be one of the poles in the closed loop. So we assume that. So if s equals j omega is going to be one of the roots of the polynomial, it means that we're going to equate this whole equation, since we've plugged it in, to 0. So this should be equal to 0. Now, since we are plugging in a complex value, we end up in a complex value. Since this is a polynomial, it's a linear operator. So therefore, we will look at the real part of this and the imaginary part, and they should be both simultaneously 0, because that's 0 in the complex plane. So all that I'm going to do is I'm going to take the real part, of pj omega equals 0, and the imaginary part of pj omega should be equal to 0 too. Now you could just create something like this in order to help yourself out for the report, and let's solve the problem here. Now you can see, by the way, I guess I'm going to display a message like Q2 here so that I know which question I'm talking about, to kind of separate them. So there we go. Now here starts Q2. These are the set of equations that we end up in, and we can see that we have 3 different solutions. Actually not different, because if you think about it, we have again omega squared somewhere. Here again is hidden omega squared, and if omega squared is a value, then we have a symmetric solution there, and it causes to basically add to the solution. But actually we just have 2 unique solutions that we're going to be interested in, and I mean this one, for example. We can see that one of them is 0 as the solution, which makes sense because this is called the origin. If you think about it, s was equal to j omega, and if s is j0, it's 0 plus j0, which is the origin itself, which is a solution. And then we have square root of 17, so j square root of 17 is a solution of this. And then there's the symmetric solution, which is negative and which doesn't make sense for us, or which is the conjugate. It doesn't actually make sense, but it's not a different solution because this is a conjugate pair. Because we have s equals j omega, we also need to have s equals minus j omega as a root, because otherwise we are not dealing with real coefficient polynomials. So yeah, now let's actually convert these values into double. So sol.k omega val equals double sol.omega, and let's come up with index where omega val should be greater than or 0, and let's say k val is equal to k val index. So I'm eliminating the negative one, basically, nothing fancy. So yeah, k val omega val, and that should be it. Now we can see one of them is 0, one of them is 4.1231, and the k interval is minus 10, 126. So it's actually not that hard to recognize that, because we can see that the second equation has a common term omega. So there's going to be one solution omega 0, and it's always going to be present. So there's always going to be a path through the origin, probably. And then we have basically omega squared is equal to 17, and you can plug it in here to solve k, and you can see that square root 17 is actually the frequency. It's not really that hard if you have pen and paper. This method might help you out. If you think about the root Hurwitz methods or all the other stability methods, it might become, or it might get out of control at some point if the degree of the polynomial increases, but here at least you have a better luck, I would say, to solve for the critical points. Yeah, so we get kind of the values that are critical to us, and we also get their frequency. So let's actually plot the root locus of this system, for the positive one, the negative one, and then also use these k values to calculate the closed loop poles and plot them on top of the root locus, corresponding root locus here. So what we can do is we can create a figure. Let's call this figure 2 because Q2. Let's have actually CLF and maybe a subplot to separate positive and negative root locuses. So CLA, hold on. Yeah, maybe AX1 and that's it. So subplot 1, 2, 2, AX2. Yeah, let's have root locus GS, AX1 GS, and AX2 minus GS. And I know that the first one is basically the negative one, so TS is going to be feedback kval first times GS, comma 1. And then we will have C poles, C zeros, PZ map. You can take different routes on this, but yeah, I'm interested in using this here. So real C poles, imaginary C poles, and then maybe black and then a higher line width than usual to have it more visible. Yeah. Maybe title, I don't know. Kval 1. And then omega maybe. Omega val 1. Of course, this is AX2. Let's repeat this whole process for the positive one. This is going to be kval 2. And then this is going to be AX1, AX1, kval 2, omega val 2. Yeah, that should be it, I guess. So let's run this. And there we go. Let's zoom in a little bit. Now we can see the following. If it's going to be 4.12, you can also click on the root locus here. And you can see it actually matches the value here. The frequency is 4 point something, so 4.12 or 4.13. This is kind of the point that we're interested in. And you can see that the gain value also matches this little dialog here. And you can see that damping is 0 because we are on the j omega axis. And yeah, overshoot is 100% because marginal stability, you would have a sine wave. So everything adds up. We can see that the conjugate is here, which is going to be the negative j omega, so negative j 4.12. And yeah, the third pole is here. Of course, it's possible to use the root locus methods to calculate the stability boundary too, but yeah, I wanted you to show that this is basically a method that numerically is very powerful if you have MATLAB available to you. The same goes for here, where you can see that this is basically the pathing through origin case here, and you have K10. Of course, this is not exactly 10, this is minus 10 because we are on the negative root locus. That's quite important to note. And you can see, well, we have one pole here and two poles are here, and the gain and everything is basically the same here. So if you wiggle it around it a little bit, you can see 10.4. Which is quite unstable, so 10 should be the value and omega should be 0, so it kind of verifies here. So of course these are the bounds, and between these two values, minus 10 and 126, we could come up with a controller that stabilizes the system. But to recap, we can see that plugging in S equals j omega is meant for the closed loop. And you can use the fact that if this is one of the roots of the closed loop, then this should be the marginal stability. Since this is a complex number, I need to look for the real and imaginary part and equate them simultaneously to 0. When I solve that, I get this. So what interesting is, and I want to share this info with you too, is that this approach can be applied to the root locus method too. We are going to see it in a moment, but in a very different way. you can use the same approach, and you could just say, okay, I'm going to plug in the desired point maybe. And by the desired point, I mean sigma is minus zeta times omega n. And omega d is square root of 1 minus zeta squared times omega n. So sigma plus j omega d, we need to run, let's run it. So sigma plus 1i times omega d is also going to be the closed loop pole, or is going to be satisfied by the closed loop polynomial. What you can do is you can substitute this instead of s and solve for the real and imaginary part equal to 0 simultaneously, and go down the route in order to come up with a controller that assigns the poles to this point. But this is an extra info, you should look into it, but I'm not going to do it here, so that's on you. And the usual way of doing it will be coming up now. So we have answered Q2, where we plug in s equals j omega, and we looked for the stability interval. This is basically the case where I generated all the data. So for report preparing, you can see I'm just leaving out some semicolons, and I will fill in the blanks and it will become a report. So MATLAB assisted homework solving is quite important for this course. So let's move on. Let's move on to Q3. So now here the question is the following. We have a desired point, which I calculated just now. This is going to be desired point. Oh, of course, I need to disp Q3 to separate stuff out. There we go. Now this is going to be the point that we want to assign the pole of the closed loop using a p-type controller. And why is that? Well, using the zeta and omega n value that we were given by the overshoot and setting time values, the result became -1 plus minus 136.44j. So this is going to be, or this is the solution to PDS, which was s squared plus 2s plus 2862. So this is basically the root of this polynomial here. Now, we need to calculate basically based on the root locus method, or in more detail based on the angle condition and gain condition, we are going to calculate the p-type controller, or design the p-type controller. Now, I talked about this in the announcement video, as far as I remember, and I said that you could use MATLAB or a little script that helps you out in doing this, rather than just coming up with the vectors and doing it by yourself. And let's exactly do that. For this purpose, I need the poles and the zeros of the open loop, so pzmap gs. You could also use gs denominator, and then this, and then roots of this, because this will give you the coefficient vector, and then you can just use this to calculate the open loop poles. Or you could stick with the pzmap approach that we do most of the time. And what I'm going to do is I'm going to come up with a distance vector. Now, the way this works is we have the open loop poles. From each open loop pole to the desired point, we need a vector. And the same goes for the zeros, but we don't have 0 in the open loop, so we're going to skip that part. So basically, desired point minus C poles is going to be what I'm looking at. So these are the vectors from each open loop pole, from this point, from this point, from this point, to the design point somewhere here. Now, this in Cartesian coordinates doesn't help me out that much, because the method itself involves using the gain and angle conditions, which is polar coordinates. So what we can do is we can convert this into polar coordinates. So let's say angle. We can calculate the angle by using a tan d, or a tan 2d. Now a tan d, you know that the inverse tangent has its asymptotes between minus pi and pi, so it will return you something between minus pi and pi, which is not quite suitable for us. We would like to have a 4-quadrant a tan function, which is atan2, where you provide, instead of providing the ratio, you provide the imaginary part of that and then the real part of the vectors, so that it comes up with, it looks up the signs and then does the job behind the scenes. So yeah, atan2 is quite nice to do. Yeah, and D stands for degrees, so it will return us the values in degrees. We can just do this, and if we run it, we see the angles 18.83, 53.76, and 90 degrees. So that's kind of where we at. But we also have, or are going to have, some gain or angle, some magnitudes here. We can do the same where we have a square root and then real part of the plus imaginary part. I'm using vector notation here because I'm dealing with vectors. I'm taking the element y square for the imaginary and real parts. I sum them up and take the square root of them. So this is basically going to be, as you can see, instead of writing down 4 plus 136, 44j, we could say 4.22, 18 degrees, 169, 53 degrees, 136, 90 degrees. So this is kind of what we're trying to do here. Now, the sum of these angles should sum up to 180 degrees if it's on the root locus. If we can use the p-type controller to assign this pole or the desired point. So let's check that. In order to check that, we could do the sum of angle and see that it doesn't add up to 180. So at this point, we can conclude that the angle condition is not satisfied. For that matter, we cannot design a p-type controller. So, and we can show that by let's just take, for example, the figure here, call it 3. Let's maybe take this part, hold on, and like that. Now let's take the root locus here, like this, and yeah, let's then plot basically the desired point. So it's going to be sigma, comma omega d, and then kx, for example, or something else. Line width 4 to showcase it even better. Yeah, so let's run this, and we have another figure. And we can see, basically, if we zoom in a little bit, it will become obvious that this point, even if it's not that far away, because 162.59 is close to 180, it doesn't satisfy, it doesn't satisfy the angle condition, therefore it's not on the root locus. So how am I supposed to click on the root locus plot and come up with a p-type controller if I'm using MATLAB's rlocus command, for example? It's not possible. Therefore, there is no feasible design here. So that's basically it. And this sets up the fourth question here, because, well, if we cannot design a p-type controller, then what should we do next in order to come up with a certain controller? We need to propose a controller based on this to come up with the solution at least. So let's actually transition into Q4. Now this part needs a little bit brainstorming, and the reason behind that is the following. We are going to propose a controller, but our angle is 162 degrees. So this would mean that we are not going to add a 0, because if we add a 0, this angle will decrease due to the fact that we take the sum of finite poles, or sum of angles of finite poles, or poles for short, minus sum of angles of zeros. So if I add a 0, it will immediately subtract from the angle, which I don't really want. So, well, if it's not going to be a 0, it seems like it should be a pole. So we should add a pole. So that's for sure. But is this going to be an arbitrary pole, or is it a special one? So this part here is crucial. And yeah, if we would have ended up in 180 degrees, if the angle condition would have been satisfied in Q3, and if we would have used the gain condition to come up with the controller, looked at the closed loop, what we would have seen would be the fact that the reference tracking would fail. Well, it would fail because there would be a distance between the reference and the output, which we call the steady state error. So therefore, a p-type controller will never help. And for step type inputs, we have step type inputs, and we want reference tracking. It would mean that we need somewhere in the loop transfer function, it may be in the controller, it may be in the open loop transfer function itself, we need a pole at the origin. Because unless we have that pole at the origin, there will be no reference tracking. There will be eventually some error between the output and input. There will be a distance in steady state. Or if we apply a certain disturbance, again, we would end up in steady state error. In order to fix this, we need to add a pole at the origin, and this one doesn't have a pole at the origin. The open loop doesn't include that, so we have to add it with the controller. So the best thing that we can add here for Q4 in order to design a reference tracking controller is going to be adding a pole. So we need to add a pole at the origin. Well, whilst we do that, I want you to remember the fact that PID controllers all have poles at the origin. They have an integrator, a pure integrator in the controller. So that's the reason why when we design a PI controller or a PID controller, we never check if the step type input is going to be tracked or not, because it will. Because we know that the type of the system is going to be 1, the amount of integrators, pure integrators is going to be 1, or the amount of poles at the origin is going to be 1 at least, and therefore we will track the step type inputs. So that's that. If we want to, for example, track ramp type inputs, we should add 2 poles at the origin, and it goes on like that. So therefore we cannot add arbitrary poles. We have to add the pole at the origin. Therefore, I'm going to do something that's not really what I need to do, but I'm going to do it anyway. I'm going to extend cpoles by 0. And then I'm going to use the same strategy here with cpoles 2. Well, why did I do that? Basically, I added the origin pole here, because that was missing up somewhere here. Don't we have that? Well, we know that these are the open loop poles. I added 1 pole at the origin. Now we can see we have a different vector, and we will have angles and gains, of course. But the sum of the angles, again, in this case, is 288. Now this was overkill. I want to reach 180 degrees, but this happened to be an overkill. Before I go on, what I want to do, whatever. Let's first solve it. We have 288 degrees as the sum of the angles. Now we did overkill it a little bit. How can we attack it now? Well, we added a pole at the origin. What we can do now is add a 0, because we now want to decrease this sum of angle. And as far as I'm adding a 0 that would contribute negative angle, I could calculate that. So at this point, the angle contribution of that should be sum of angle minus 180. like this. So there we go, 108 degrees. So is this possible? Of course, because you can see if I added a pole at the origin, I added 126 degrees. So it should be a little bit to the left of the origin, somewhere here. I should add the 0 to have 108 degrees of angle contribution, of course negative. So then the difference of the pole and the 0 is going to be something around 17 degrees, which was necessary to meet the angle condition at the first place here. So yeah, we need to add this 0 for this angle. Now, what would this mean? Well, we know what the imaginary part of this is, and we know the angle. So we could use tangent, so tan d theta z. We could use this, which would be equal to omega d, which is the imaginary part of our design point, since we are on the real axis, since we're adding a 0. And that divided by dz, which is going to be basically the real part of the distance vector, rather than the 0's exact location. Now, of course, we have to swap out dz and tan d in order to solve for dz. And it would look like this. Minus 0.4654. This actually aligns with the fact that this is minus 1 as far as I remember. It should be to the right of minus 1. So negative distance means that we're on the right of this place, because then we have this wide angle of 180 degrees. So it makes sense. It aligns with the fact that the distance is negative. So I can now calculate the position of 0, which is going to be basically sigma, and then plus the distance, I guess. So let's run it. Minus 1.46. I guess that should be minus dz. Yeah, that makes more sense. The reason why this makes sense is that it should be between 0 and 1, between the origin and between 1, which is sigma here. So therefore it should be in this interval somewhere here. And since this is z, I'm going to use the absolute value here, because I think about s plus z instead of the 0 itself. So therefore this should be the polynomial coefficient instead of the 0 itself. So s plus 0.5346 is equal to 0, so s is minus 0.5346, which is exactly the point that it should be at. Yeah, this is basically the location of the 0. The only thing that is left is, and I'm going to repeat something here, that would be the desired point minus minus z, because minus z is the 0. So dz is going to be this. So let me show it here. So this is going to be the distance vector from the 0 to the destination point, so to the desired point. And what I can do now is I can use the angle condition again, but then I'm going to subtract the angle of dz. So this should give me this, and it's actually the sum of this minus 180 degrees. So I kind of double checked if this really works, if dz is correct. And you can see when I add a pole at the origin and then subtract add a 0 at that exact location, then I end up in 180 degrees, which seems like it should be working. Now for the gain, I'm going to do the same, but I need the product of this vector here divided by the same thing for DZ. So let's run it again. And we can see that this is going to be the gain value here. So I'm going to do the following. Let's open up a figure here, figure 4. Let's have subplot 2 to 1 CLA. So hold on, AX1, GCA, or don't even bother with that. So I'm going to plot the root locus here. Well, first of all, we had GS. Okay, let's go with this. And yeah, we added basically a pole at the origin. So when you're plotting the root locus, you should basically do this, repeat this here. And let me take this one here. There we go. Now, since the p-type controller case is already addressed, I'm not going to repeat that part, but we looked at the angle, we looked at the system and the controller structure, and we decided on the fact that we should add a pole at the origin, or a pure integrator. Now, when we did this, we actually altered the dynamics of the loop transfer function that we are interested in. Therefore, the root locus plot is not going to be of GS, but since we added another pole, it would be the root locus of GS times that pole. So this is going to be generating that plot. And we then added a 0, since that was necessary. And then we ended up in this here. And here I'm going to basically define the controller itself. Like this. And maybe also open up a grid on title step response, or pulsar map. It could be pulsar map. Let's have pulsar map. Let's don't have grid on. Yeah, let's define the remaining or the actual controller, the resulting controller. It should be kval times tf, the 0, 1z, and then the pole 1, 0. And then we have gs, so let's create ts, feedback fs times gs, 1. We can acquire the poles, the zeros, pz map, ts. We can then plot the real part of c poles, imaginary part of c poles, and then kx, and then line with 2. We can repeat this for the zeros with ko, and then we could also take this part here. Let's make it red because that's the desired design point. And let's have another maybe s grid for zeta and omega n, and then subplot 4 where we have basically the step response. I'm just basically summarizing stuff here, and that's going to be yt step ts plot t comma y k line width of 2. Info is going to be step info ts, and then TSE is going to be info dot settling time. OSE is going to be info dot overshoot, and then let's alter the title here. Let's say ts plus string ts, and then os plus string os plus percentage. So yeah, this should do it basically. Let's run it. And we messed up. What is kval? Oh, it's actually called gain for some reason. There we go. Maybe a little grid on would be nice here. There we go. Now, let's zoom in a little bit and let's see. Now, the first attempt was to add just a pure pole due to the fact that we wanted step type reference tracking. Now, this was an overkill where you could see that this was really off. And then we added a 0 in the vicinity here. And you can see that we fixed it right away. And now this point is accessible on the root locus plot. Now at this point, we added 1 pole and a 0. So therefore this dynamic part is added to the system's open loop. Now we have a totally different kind of open loop where we are looking for a p-type controller. So that's what we have reduced down to. Yeah, therefore we we did then verify that the angle condition was satisfied with 180 degrees. And then we also used the gain condition in order to calculate the appropriate gain that is necessary to assign this to. Now, this is the closed loop pole zero map where we can see that these two were actually the desired poles. Whereas our 0 is on the right, our pole is on the right at the end of the day, and we have a pole that is somewhere here. Now, in terms of dominant pole assignment, it doesn't look good. We would have liked to have them closer to each other, so this should be a near perfect pole zero cancellation to be able to have the better, or to be able to have the desired specifications of the system. But other than that, this is the best that we can do. There's no other choice. And we actually designed a PI controller without even noticing it, because we needed the integrator, we added that. We needed to match the angle condition, we added the 0. And we ended up in designing a PI controller. And we can see that the pole from the origin and the 0 of the PI controller caused some issues. We would have liked to have a better pole zero cancellation, because this part here is kind of a lag part, a phase lag controller part, where in fact a PI controller is a phase lag controller, so there's no trouble or bad thing about that. But lag controllers have this strange behavior where, since they are the slower part, if the cancellation is not better, we kind of end up in this transient, which is basically over here somewhere, 4, and then the lag part just acts upon the system and drives it to 0 steady state error. So this is not the best case scenario, because, well, the PI controller is what it is, and this is the best it can do for these specifications. But yeah, we might want to just update the structure of the controller, maybe opt for a PID controller or whatever. But we could also maybe look at our design specifications, because clearly the system is having trouble to reach that point. And also, this is not the ideal shape or curve that we get from a 10% overshooting system. It kind of seems like if we wouldn't have added this lag part here, the system would have a steady state error to some degree, and yeah, it would give us a certain overshoot, maybe not the settling time, so, or reference tracking. Yeah, this is the best we can get for this controller here. If you design a lag controller without placing the original pole at the origin, then you don't have reference tracking, and that would cause some issues. Of course, it could be it would align with these results to some degree, but you probably wouldn't see this behavior here, because there will be no pure integrator in the controller. So yeah, this is specifically the answer that we would look for if you go through this path of trying to add a pole due to the type of the system, and then fixing it with a 0. You would end up at this place. So let's actually move on to Q5, which is the last question, but which is kind of repeating Q4, because we're going to design the same controller, but using the algebraic method. So let's do that. Now, if we are going to design this, we sort of have already PDS as far as I remember. Yep. So we need to work our way out. So let's start with the controller definition. The controller is going to be Kp times S plus Ki divided by S. Now you might be wondering why I'm using Kp Ki here instead of using K times S plus Z divided by S. Now the definition here looks more likely for a root locus method, because we see what the pole is, we see what the zero is, and then we look for the p-type part of this controller here. You could use this, but you should remember that Z is going to be the zero and K times Z is going to be in your equations, and therefore I don't really recommend you to use that. If you're using the algebraic method, if you're using the polynomial method, then what you should do is you should stay linear as much as you can. Here we can just skip the whole times K times Z part when we define Kp and Ki like this. This is the proportional part, this is the integral part, that's it. Now we are going to look for the closed loop, which is exactly FSS times GSS and then divided by +1. Of course, now PZS makes more sense because we have a zero, but we're not going to focus on that. So now we have PCS. Now we can see that this is a fourth order polynomial, and yeah, the highest order term has coefficient 1. So we need to define a residual polynomial. And again, here we could define it like P1 and P2. And it would look like S plus P1 times S plus P2. But I don't really like to do this. I would discourage you to do this because I can go ahead and define it like this, which is much cleaner and again, much more linear. Here I can claim that A and B are real values because these are coefficients of a polynomial and we always work with real coefficient polynomials, so that's not big of a deal. But you cannot claim the same for P1, P2 because they could be complex conjugate pairs. So the only thing that you can claim here is that P1 and P1 conjugate is going to be the thing that we are looking here. So that's the only thing that we can do here. And then you would have P1 plus times P2 and P1 plus P2 in your terms. When you combine it with K times Z, it will be becoming a nightmare because you are complicating stuff that shouldn't be complicated like that at all. Now, we can then have the problem, we can state the problem, which is going to be coefs of PCS, all the coefficients of PCS, should be equal to all the coefficients of PDS times PES. And since we're at it, we can just use one length problem and then disp VPA problem I, comma 4 in order to show each equation on its own. Then we could also solve for problem. Let's run it. Now we can see that just by eyeballing it, we can solve the equations. A is going to be 6. This is going to be 12. This is going to be 5. 5 minus 2.862 is going to be B. And I know that this is 6. 6 times 2.862 plus 2 times the value B. It gives me Kp plus 10, so Kp can be worked out. And then Ki is 2.862 times B. So it's not that hard to compute these values. And you can see that everything is linear. So there's no nonlinearity at all. And the reason behind that is the left part here is linear in terms of Kp and Ki. The right hand side is going to be linear in terms of A and B because A and B are the unknowns of the residue polynomial, but this is going to be multiplied with PDS, which is a known polynomial, so it doesn't create a nonlinear part. If we wouldn't know what zeta or omega n is, or both, then this would be a nonlinear part. This would include a nonlinear part, but that wouldn't be that big of a deal. But it would just be a little bit more tougher than it is now. So we can basically convert everything into double, and we have only one choice. We don't have multiple choices here. So yeah, let's have a-val double sol.a. Repeat this for b. And then kp-val is going to be double sol.kp, and the same goes for ki. I'm using placeholders, not the actual variables, because we might end up in using them again. So let me write down what the controller is: kp-val, ki-val, 1, 0. We could also show the ZPK form, and then ts is going to be feedback fs times gs, 1, and then again ZPK TS. So there we go. We can see that the location of the zero is again the same, 0.5346. The gain value is going to be the same, and our closed loop transfer function ZPK form looks again the same. We have the desired pole, we have the almost cancellation, 0.38 and 0.53, and then a faraway pole, 5.619, which are all shown in this pole zero map. And of course, since this is the same design, we will get the same step response. But here you can see that the algebraic method can be used to design controllers, and the root locus method can also be designed or used to design controllers. And they have kind of this viewpoint difference, because one of them looks at poles and zeros in terms of angle condition. It kind of tries to bend the whole root locus plot so that we pass through the desired point, and then we try to come up with a controller, and that's it. Where on the other hand, we are just looking at the system. We come up with a polynomial, then we add a residue polynomial to match the degrees of the polynomials. We take the multiplication and then look at the coefficients, and we equate them to each other, and we solve it. The algebraic method does it kind of blindly, out of nowhere, if you look at it in terms of poles and zeros. But yeah, you can get both solutions from different angles by attacking it with different tools, but you will end up in basically the same solution here. So yeah. And when I talked about solving the homework using MATLAB Assistance, this was exactly what I was talking about. As you can see, we didn't use pen and paper, we didn't use any calculator. We have just MATLAB anti-symbolic toolbox, and we can just generate whatever we want, however we want. So we did that exactly. Yeah, I also have actually, let me find it somewhere here. I should have also a solution manual that I might like to show you. Yeah. There we go. So let's take a peek view. There we go. Now, let's recap actually, because we did a lot of things. The first question was about designing an open loop controller, and I directly took the denominator of the system, placed it as the numerator of the controller, placed the desired polynomial in the denominator, and then the omega n squared, because omega n squared divided by omega n squared, it should be equal to 1. And if I multiplied this with the actual system, this should vanish, and we would end up in omega n squared divided by s squared plus 2 zeta omega ns plus omega n squared. This is kind of a mixed match of control with the inverse of the system and our kind of desired polynomial approach here. And you can see when we plug in these values, we get basically the same result that we talked about in this video. And ideally, when you multiply them, these should go away and you would end up in TDS or TS, which is basically this transfer function. And if you apply step to it, of course, you will get 3.5 seconds or 4 seconds of settling time with 10% overshoot. So yeah, this was the first question. In the second question, we were asked to calculate or obtain the stability interval of this system, of the open loop system. We used the p-type controller, we calculated the closed loop transfer function, and then we assumed that the closed loop polynomial, characteristic polynomial, which is this one here, should have a pole on at the j omega axis. So it should be pure imaginary. Therefore, we defined it as s equals j omega, but we didn't know where this would happen at which exact omega value this would happen. So we left it as unknown. We plugged it in and we assumed that this should be equal to 0 if it's satisfying this polynomial, if it's a root of this polynomial. Therefore, we took the real and imaginary parts of this complex valued function, and then we examined it in terms of omega and k, and we ended up in two different solutions or cases, one of them being a path through origin, one of them a path through the j omega axis as a pole pair. And then we calculated basically the values. I guess this one is a mistype, so it should be 126 and minus 10, not 46. And you can see that one is on the negative root because we've shown it in this video, but not in the PDF. And we have another point here, which is square root of 17, where you can see the value of that. The third question was about the p-type controller. Let's design a p-type controller that go throughout a certain point that is going to be this, because this is the solution to PDS, the desired polynomial. Now, from each open loop pole to this point, we have calculated the difference vectors, or the vectors. We've converted them into polar coordinates, and that's actually it in order to design a controller using the angle and gain conditions, because you sum the angles, and if it's satisfying the 180 degrees property, then you can just multiply them and you have the gain. If you have zeros, of course, that should be taken into account differently, but we don't at this point, so that would be it. But we can see that 162.5952 is not 180 degrees, so it's not on the root locus plot, so there's no p-type controller that achieves this pole in the closed loop, so therefore we have no feasible solution at all. Now, therefore, based on this, we were asked to propose a controller. What we did was we just added an integrator, a pure integrator, or a pole at the origin, due to the fact that we wanted a reference tracking. And since if the system's loop transfer function is type 0, it would end up in a steady state error. It should be type 1 in order to track step type inputs. It could be type 2 if we want to track ramp type inputs, and type 2 means a double integrator at the origin. So that's going to be basically it. If that would have been the case, we would have added 2 poles here, but for this case, it's only step type inputs, so we added just 1 pole. Adding 1 pole ended up giving us the sum of angles as 288 degrees, which was an overkill, which was too much. So we used a 0 to compensate that, and since we added 126 degrees with a pole, it would be imaginable to add 108 degrees of angle contribution with a 0, which is not exactly at the origin, but a little bit to the left. So yeah, adding the 0 at this angle, we use the tangent, and we know that the imaginary part is this, so the tangent should be like this. We calculated the exact position of the 0 to be here. Then we used the gain condition. Actually, in this video, we also have looked at the angle condition and verified that it works actually. And then we looked at the gain condition and we ended up in 11.4461. The resulting PI controller looked like this. The resulting closed loop transfer function, pole 0 map, they look like this. Unfortunately, the values didn't end up being what we expected them to be. So we ended up in 7.77 seconds settling time and 0 overshoot. That was because of the almost cancellation that we had here. And the effect was kind of a lag controller effect, the phase lag controller effect, where PI controller, of course, is also a phase lag controller, but it has this reference tracking property because of its pure integrator or a pole at the origin. So therefore, We didn't quite get what we wanted, but yeah, this was the best that we could achieve at this point. And you can see up to this point, our actual transients kind of show it themselves, but then the lag controller takes action because it's even slower than everything else. So we see that it kind of forces the system to zero steady state error. And that's basically it. We then also looked at the alternative solution of Q4, which was designing a PI controller for this system, where we had this desired polynomial. We looked at it as a pole. Now here it's a polynomial. It's basically the same data all over again. We came up with a residue polynomial with linear coefficients. We defined our controller in terms of linear coefficients. That's quite important at this point. If you don't do this, if you just use k, z, and p1, p1 conjugate, then you are just over complicating stuff. So yeah, that's not necessary. You can see this is nice and linear, and we solved it, and we've seen that we have no other choice than designing this controller because there's only one solution that we can get with a PI controller. There is an exact angle contribution that we are looking for, and if we fix the pole at the origin, then there's just 1 0 that will give us the exact amount of angle contribution that we are looking for. So that's the reason why we can only design this PI controller. In terms of report preparing, this is of course just a quick solution manual that I've prepared for myself. Because after weeks, one might forget what the solution looked like. So if I would have been a student, I would have prepared a little bit more details, or rather, I would just add these plots to the PDF and document it a bit better to get a better report. This is kind of a reminder sheet for myself, so it's also not bad, but yeah, it could be a little bit better than this. But yeah, this should give you an idea about how you should prepare your reports at this point if you still didn't get the idea. As you can see, we've used MATLAB assistance and only MATLAB assistance, nothing else. A little bit, of course, is upon you when you have to decide for stuff. You should go for the right decision, and that takes some studying and some experience, of course. But other than that, hope that this was helpful for you, and hope that this kind of gave you a throughout solution, a guide to throughout the solution. And yeah, see you in the next homework.